When a water treatment plant fails, the signs are aggressively physical. Reverse osmosis membranes clog, forcing pumps to work overtime as system pressure drops inexplicably. The mechanical strain is obvious, but the culprit is often invisible to the naked eye. We are dealing with chemical oxygen demand, or COD. COD measures the exact amount of oxygen required to chemically obliterate the organic waste present in your water supply. To gain control of your plant, we need to do two things. First, we will execute a precise laboratory closed reflux COD test. Second, we will deploy a strict 4-step troubleshooting protocol for when those test numbers read dangerously high. Tracking COD is a strict regulatory requirement, but more importantly, it is your primary defense mechanism to keep your RO and zero liquid discharge systems from choking on their own organic waste. Step 1 is sample preparation. Draw exactly 2.5 milliliters of your water sample into a clean COD vial. For RO feed water, your strict baseline limit is under 10 to 20 milligrams per liter. Anything higher is a threat. Now we add our reagents. First, inject 1.5 milliliters of potassium dichromate. This acts as our primary, highly aggressive oxidizing agent that will directly attack the organics. Next, add 3.5 milliliters of sulfuric acid reagent. This creates the highly acidic environment required to force the oxidation reaction to occur. Mixed within that acid is silver sulfate. It serves as a crucial catalyst, drastically accelerating the chemical breakdown of the waste. This abstract logic model shows how we handle interference. The mixture contains mercuric sulfate, which binds directly to naturally occurring chloride ions. If left unchecked, those chlorides would oxidize and give you a falsely high COD reading. A brief but mandatory safety stop. You are handling heavy metals and highly concentrated corrosive acids. Strict personal protective equipment, including gloves, safety goggles, and a lab coat, must be worn at all times. With the prep complete, you have a precise chemical cocktail explicitly designed to strip away false variables and force the true organic load of your water to reveal itself. Secure the cap tightly on the vial and place it into your COD digester. Set the mechanical parameters to exactly 150 degrees Celsius for a 2-hour cycle. Inside that vial, an aggressive reaction is underway. The extreme heat, combined with the strong oxidants, are systematically burning up every organic compound present. After the 2-hour digestion phase, turn off the heat. You must let the vial cool completely to room temperature before you attempt to take any measurements. Look at this side-by-side comparison of 2 laboratory vials to see the colorimetric measurement method. Using a spectrophotometer, you can determine the concentration based on hue. The highly transparent liquid shows clean water, while that dark, opaque green mathematically correlates to a dangerously high COD level. Alternatively, you can use the titrimetric method. By titrating the sample with ferrous ammonium sulfate, you watch for a distinct color shift from blue-green to reddish-brown, allowing you to calculate the precise load. Whether measured by light absorption or chemical titration, this final color change transforms an invisible organic threat into clear, actionable data. So, what physically happens to your plant infrastructure when that data reveals COD limits exceeding 20 milligrams per liter? Here, organic biofouling creates a thick slime layer sealing the RO membrane's pores. Differential pressure spikes from 1.2 to 1.6 bar, killing permeant flow. Downstream in the ZLD evaporator, boiling triggers severe foaming, ruining heat transfer and destroying system vacuum. A high COD number is the direct, verifiable cause of mechanical strangulation across the entire treatment facility. When a high COD test is confirmed, you must initiate a 4-step emergency protocol to restore system stability. Action 1. Inspect the activated carbon filter located upstream of the RO. Backwash it immediately to clear trapped organics. If the carbon media has reached exhaustion, replace it entirely. Action 2. Move to the biological system, like your aeration tank. Verify your dissolved oxygen and MLSS levels. The bacteria here consume COD. If those bacteria are dead or starving, the organic load passes straight through to your filters. Action 3. Conduct a jar test. Use the results to increase the dosing of coagulant and flocculant in your primary clarifier. This forces suspended organics to clump together and settle out early in the process. This instruction card shows the exact chemistry needed for Action 4. If your RO membranes are compromised by slime, Execute a high pH alkaline cleaning in place. Using sodium hydroxide and EDTA at a strict pH of 10.5 to 11.0 will chemically dissolve the organic blockage. By following this protocol, you replace panic with a methodical, step-by-step elimination of organic threats across the entire treatment train. The operational payoff is clear. Driving COD back below that 20 milligrams per liter threshold ensures your plant's structural integrity is protected. Your RO membranes stay completely clean, differential pressure holds steady, and your total water production quality remains at peak efficiency. Integrate this closed reflux methodology into your daily laboratory routine. For a deeper breakdown of how to rescue fouled filters, check out our upcoming video on perfecting alkaline CIP procedures. Mastering COD analysis takes the guesswork out of water treatment, elevating you from reactive firefighting to proactive scientific plant control.